Let's have a look at this question. The heat of combustion at decant, formula is given, is 44.2 megajoules per kilogram. Another name for this, which they use in some question, is energy density. So sometimes they just say the energy density of decant is 44.2 megajoules per kilogram. So energy content is the other name that you can use. And this is measured under SLC. Let's just highlight that. I'm not sure how that's going to come into the question just yet. Based on this information, calculate the molar heat of combustion of decant. So molar means per mole. So you need to determine the heat of combustion per mole of the fuel. And one other thing that you should notice here is that the question doesn't specify a unit that you need to leave your final answer in. So obviously it's per mole, but the question doesn't say that it has to be in kilojoules or megajoules or joules. So when the question doesn't tell you, then any correct unit is acceptable. So it doesn't matter if you leave it in megajoules or in kilojoules, as long as the value is correct. So in order to determine the energy, the molar heat of combustion, or the energy per mole, you need to basically make the conversion from mass to mole, because you're given the energy content per kilograms, which is mass. So the mass of decant is a kilogram, which is the same as 1,000 gram. And I need to convert this to number of moles. So you just need to find the molar mass using the data book or the periodic table, to be more specific. Although I do hope that by now you know that each carbon is 12 and each hydrogen is 1. So that would be 100 and, oh my god, I can't do anything. Okay, 120, 140, Jesus, 142. I did have that in my head in my defense. You don't need to believe me. But just in case I make a mistake and I have to record another video. So the number of mole of decant, it's going to be mass over molar mass. If you need to draw the triangle out, you can. So let's just do it here. Mass, number of mole, molar mass. Really do hope that you remember it by now. So it is 1,000 grams divided by 142 grams per mole. So 1,000 divided by 142 is 7.04. Now you want to keep the actual answer in the calculator, but I'm just going to write to correct the three significant figures here. So 7.04. And then from here, I can convert 44.2 megajoules per kilogram to the value in mole. So basically, you know that 44.2 megajoules is the amount of energy in 1 kilogram, which is the same as the amount of energy in 7.04 mole, since this is the number of mole of 1 kilogram. So if you divide one by the other, you will have the amount of energy released per mole. Now you want to keep the exact value in the calculator. So 6.28 megajoules is the amount of energy per 1 mole. So I'm gonna do final answer, molar heat of combustion. Now remember that heat of combustion is just a value, so it shouldn't have a negative sign. If the question asks for molar enthalpy of combustion, which is delta H, then you need to put a negative sign here, but you don't have to for this question. So 6.28 megajoules per mole. You could also convert it to kilojoules if you want. So 6.28 times 10 to the 3 kilojoules per mole. But you don't have to. So either answer is fine. You can convert it to joules if you want, but I don't know why you would do that. So that's part A. And then let's look at part B. Write a thermochemical equation for the complete combustion of decant. All right, so this is why SLC is mentioned, because it tells you that the state of H2O must be liquid. I don't know why I always act surprised when I record these videos. Oh, this is why this is mentioned. I mean, I wrote the question in myself, but anyway, so thermochemical equation means that you need an equation, a balanced equation with state, and also you're going to need to include delta H in the final answer. So don't forget that. That's the difference between an equation and a thermochemical equation. So the first thing I would do is I'm just going to set up the equation. So this is a complete combustion. The state of decant should be liquid. I think it's too heavy to be a gas. Oxygen is a gas, obviously. CO2 is a gas. And H2O, because this is measured under SLC, must be liquid. So step 1, set out the reactants and products for a complete combustion reaction, which should produce carbon dioxide and water, or steam. Sorry, in this case, actually liquid water. And then I'm going to balance it. So you want to start by balancing carbon. So there are 10 carbon atoms on the reactant side. So I'm going to put a 10 here. Excuse me. And then you need 11 hydrogen, 11 in front of the water to get 22 hydrogen atoms, which means that you're going to get 22 plus 11, which is 33 oxygen atoms on the product side. So I'm going to add 33 over 2 as the coefficient on O2 on the reactant side. So this is my balanced combustion equation. If you don't like fraction in your coefficient, you can just double everything and then that will get rid of the fraction. So you can get 2 of these. Don't forget state plus 33 O2, giving you 20 CO2 and 22 H2O. So that's an alternative answer. Either answer is acceptable. The only thing that will change between one answer and the other is the value of delta H. So we already calculated the molar heat of combustion from the previous question, so you can just use it, except that you have to make sure that you add the negative side, because we're talking about enthalpy here, which should be negative for combustion since it is an exothermic reaction. The unit is kilojoules per mole. I'm going to leave it as kilojoules. You know, I'm not even sure whether it's acceptable to leave it as megajoules, so I'm not going to do that. However, if you double the coefficient of the fuel, you also need to double this value. So if you want to go with the second option, then the delta H value, that should have a H here, the delta H value will be negative 1.26 times 10 to the 4 kilojoules per mole. So this is correct scientific notation. If you write it as negative 12.6 times 10 to the 3, I think it's fine, because scientific notation is technically not required. So just something like that. Okay, so just make sure that if you change the coefficient of the fuel, if the coefficient is not 1, then you can't just use the molar heat of combustion. You would have to use a multiple of that. So that's part B. Let's hope we didn't make a calculation error. Let's move on to part C. Calculate the energy density in kilojoules per liter given the density of decane. So I think this probably is the hardest question out of the three, because people are not very comfortable with density, but it really just takes practice. So you're going from mass to volume here. You're going from energy per mass or per kilograms to energy per volume or per liter. So what I would do, which is going to be very similar to what I did in part A. So in part A, we're just going to go back. In order to go from per mass to per mole, I basically find the number of mole in 1 kilograms. So I'm going to do the same thing, but in this case, I'm going to find the volume of 1 kilogram using the density. So mass is C10H22 is 1 kilogram. What is that? 1 kilogram, which is the same as 1,000 grams. So that's the mass, and I need to find the volume. Now the density is given to be 0.730 grams per mil. Yeah, so which is the reason why I convert the mass to grams, so that it matches the unit in the density formula. So that means that if I have 1 mil of the fuel, it will have a mass of 0.730 grams. And then the question that we want to answer here is that if I have 1,000 grams, what volume would it have? So in order to find x, you just basically need to divide 1,000. What is this? 1,000 by 0.730. So 1,000 divided by 0.730 is 1,369 mil. I'm going to convert it to liter. So 1.369 liter. Keep the correct answer in your calculator so that we actually do the routing at the end. But I'm just going to leave it at, it's actually 370 if you look at, if you route it properly. Let's just leave it like that, 1,370. But I'm going to go with the exact value in the calculator. Okay, so we know that 44, where did the mouse go? Okay, 44.2 megajoules is the amount of energy that's released from the combustion of 1.370 liter of the fuel. So you need to just divide one number by the other to work out the amount of energy that you will get from combustion of 1 liter, which is 32.3 megajoules, and then convert it to kilojoules. So energy density is going to be 32.3 times 10 to the 3, converting to kilojoules. I think I can fit it in here, kilojoules per liter. All right, so that's energy density. I didn't add a part D, but if you want, you can also try to think about how you would go from energy density back to energy content in kilojoules per or megajoules per kilogram. So can you comfortably convert between one unit to the other? That is that for question 1.